binary number system, decimal number system, octal number system, and the hexadecimal number system. Okay, and also we have seen the different Boolean laws, and also we have seen the different rules of Boolean algebra. Okay, so these are the different rules, basic rules of Boolean algebra. The first rule is that a plus 1 is equal to a, means that when a variable is odd with 0 is always equal to the variable. Okay, the input variable a is 1.
You are not audible.
Okay, hello, hello. Okay, now I'm audible.
Yes, sir.
Yes, sir.
Okay. So rule number 1 was a plus 0 is equal to a. Means what? When a variable is odd with 0 is always equal to the variable. Okay. Means if a is odd with 0, then it is equal to a. That can be seen by using this logic diagram also. So here we are having the OR gate. So the lower input of this OR gate is fixed to 0 and the a is equal to 1. We have taken a is equal to 1. So 1 plus 0 is equal to 1. And here we have taken a is equal to 0. So 0 plus 0 is equal to 0. So when the variable is odd with 0, it is equal to the variable. Okay. The next rule is that when a variable is odd with 1, is always equal to 1. Okay. What is this rule number 2? When a variable is odd with 1 is always equal to 1. Means a plus 1 is equal to 1. Here we have taken the OR gate. So lower input of this OR gate is fixed to 1 and the value of a is equal to 1. Then the output is equal to 1. When the value of a is equal to 0, then also the output of x is equal to 1. Means when a variable is odd with 1 is always equal to 1. Okay. This is rule number 2. Next rule is that a dot 0 is equal to 0. What is this rule? When a variable is odd ANDed with 0 is always equal to 0. Means a dot 0 is equal to 0. So here we have taken the AND gate. So lower input of this AND gate is fixed to 0 and the value of a is equal to 1. Then also the value of x is equal to 0. And if the value of a is equal to 0, then also value of x is equal to 0. Means it states that when a variable is ANDed with 0 is always equal to 0. Okay. Next rule number 4 is that a dot 1 is equal to a. Means when a variable is ANDed with 1 is always equal to the variable. So here we have taken the lower input of the AND gate is 1. And if a is equal to 0, then the output is equal to 0. That is equal to the variable. When a is equal to 1, then the output x is equal to 1. That is equal to the variable. Means when a variable is ANDed with 1, it is always equal to the variable. Next rule number 5. Here we have when a variable is odd with itself is always equal to the variable. Means a plus a is equal to a. Means if a is equal to 0, then 0 plus 0 is equal to 0. If a is equal to 1, then 1 plus 1 is equal to 1. So where both the inputs are same variables, the output is equal to the variable. Okay. So rule number 5 is that a plus a is equal to a. Next rule number 6 is that a plus a bar is equal to 1. It states that when a variable is odd with its complement is always equal to 1. Means if A is 0, then 0 plus 0 bar is equal to 1. And if A is equal to 1, then 1 plus 1 bar is equal to 1 plus 0 is equal to 1. Means when a variable is odd with its complement is always equal to 1. The next rule number 7 is that A dot A is equal to A when a variable is ANDed with itself is always equal to the variable. Means if A is equal to 0, then 0 dot 0 is equal to 0. If A is equal to 1, then 1 dot 1 is equal to 1. Here you can see that when a variable is ANDed with itself is always equal to the variable. Here we are using the AND gate and we are taking the values of A is equal to 0 and A is equal to 1. Then when the variable is ANDed with itself is always equal to the variable. Then rule number 8 is that A dot A complement is equal to 0. So when a variable is ANDed with its complement is always equal to 0. So either A or A bar will always be 0, and when 0 is applied to the input of the AND gate, the output will be 0. So rule number 8 states that A dot A bar is equal to 0, means when a variable is ANDed with its complement, it is equal to 0. Then we have rule number 9 that states that A is equal to A double bar, means a double complement of the variable is always equal to the variable. Means if you start with the variable A and complement invert it once, you get A bar, and if you then take A bar and complement invert it, you get A, which is the original variable. Means A is equal to A double bar. So that is shown by using the inverters. So if A is equal to 0, and the output of the NOT gate is equal to 1, and when this 1 is given as input to the other gate, then the output is equal to 0. Here again we can take A is equal to 1, then the output is 0, and this 0 is again given to the NOT gate, so output is equal to 1. So A is equal to A double bar. Then rule number 10 we are having that A plus AB is equal to A. So this rule we can prove by applying the distributive law and rule number 2 and rule number 4. So first A plus AB, then we can take A common, then we get 1 plus B. So this is the distributive law. Then we know that 1 plus B is equal to 1 by rule number 2. So A dot 1. Then by rule number 4, A dot 1 is equal to A. So that is equal to A. Hence we can prove that A plus AB is equal to A. So this proof is shown by using the truth table and the logic circuit. So here you can see that A is equal to A plus AB. Okay. And here we can see the logic circuit for that. And next rule number 11, A plus A bar B is equal to A plus B. How to prove this? So this rule can be proved as A plus A bar B is equal to what? We can take A is equal to A plus AB from the rule number 10. Okay. Then by rule number 7, A is equal to A dot A. So we can replace A by A dot A. Then we can add A dot A bar is equal to 0 by using rule number 8. Okay. So after that, if you do the factoring, then you get A plus A bar into A plus B. Okay. That is equal to A plus A bar is equal to 1 by rule number 6. So 1 dot A plus B. So if you drop the 1 by rule number 4, that is equal to A plus B. So this rule number 11 we can show by using the truth table. So here we can see that A plus A bar B is equal to A plus B. This is the truth table and this is the logic circuit for the same. Then rule number 12 is that A plus B in the bracket into a plus c is equal to a plus bc. So how to prove this? So this rule can be proved as a plus b into a plus c is equal to a into a dot a into c plus ac, a into b ab, b into c bc. This is the distributive law. Then a into a is equal to a by rule number 7. Okay. So we have taken a common into 1 plus c. 1 plus c is equal to 1. So a dot 1 is a dot 1 plus ab plus bc. Again a is taken common 1 plus b. By rule number 2, 1 plus b is equal to 1. So it is a dot 1 plus bc. And by rule number 4, a dot 1 is equal to a. So that is equal to a plus bc. So in this way, we can prove the rule number 12 that a plus b into a plus c is equal to a plus bc. Here we can see the truth table and the logic circuit for the same. A plus b into a plus c is equal to a plus bc. Okay. Next is what is De Morgan's theorem? Okay. So De Morgan's theorem De Morgan proposed two theorems that are very important part of the Boolean algebra. So in the practical terms, this De Morgan's theorem provides the mathematical verification of the equivalency of the NAND gate and the negative OR gate, and the equivalency of the NOR gate and the negative AND gate. Okay, NAND and negative OR, and NOR and negative AND. So one of the De Morgan's theorem is that the complement of product of variables is equal to the sum of the complements of the variables. Okay, the complement of the product of variables is equal to sum of the complement of the variables. So that can be written by formula, that is xy bar is equal to x bar plus y bar. Okay, so it can be stated in another way that the complement of two or more ANDed variables is equal to the OR of the complement of the individual variables. Okay, so xy bar is equal to what? X bar plus y bar. So De Morgan's second theorem is that the complement of a sum of variables is equal to the product of complement of the variable. Okay, the complement of sum of variables is equal to product of complement of the variables. That is xy bar is equal to x bar dot y bar. Okay, so it can be stated as the complement of two or more odd variables is equal to the AND of the complement of the individual variables. Okay, this is the De Morgan's theorem. First is that xy bar is equal to x bar plus y bar, and second is x plus y the whole bar is equal to x bar dot y bar. These are the two De Morgan's theorems. Next, here we can see the gate equivalencies with the corresponding truth tables that illustrate the De Morgan's theorem. Okay, so NAND is equivalent to the negative OR, and NOR is equivalent to the negative AND. So we can see the circuit diagram, that is the gate equivalency and the corresponding truth tables for the same. Here we can see the examples of the De Morgan's theorem. We have to apply the De Morgan's theorem to the expression x, y, z the whole bar is equal to what? X bar plus y bar plus z bar. Okay. And we can apply this De Morgan's theorem to the expression w, x, y, z the whole bar is equal to what? W bar plus x bar plus y bar plus z bar. Okay. Next, we are having what is the code conversion. Okay, so what is the code converter? Code converter is used to convert one type of binary code to the other. Okay. The code converter is used to convert one type of binary code to the other code. There are different types of binary codes like the BCD code, gray code, XS3 code, etc. Okay. So these different codes are used for different types of digital applications. Okay, so code converter is used to convert one type of binary code to the other type. Next, what is the BCD code? So BCD stands for binary coded decimal. So it is the simplest binary code for the decimal digits. Okay. So here we can see that the decimal is written and the BCD code for that. So only encodes 10 digits from 0 to 9. Okay. So BCD is a weighted code. So the weights are 8421. Same weights as for the binary numbers. There are 6 invalid codes, that is 1010, 1011, 1100, 1101, 1110, and 1111. Okay. The examples of the BCD code for 13 decimal is 0001, 0011. Okay. BCD is the binary coded decimal. Next, what is the gray code? Okay. And how to convert binary to gray and gray to binary. So these gray codes are also known as a reflected binary code. Reflected binary code or gray code is an ordering of the binary number system such that the two successive values differ in only one bit position. Okay. What are the gray codes? They are also known as the reflected binary codes. So the two gray codes differ by one bit position. Okay. Differ in only one bit binary position. So these gray codes are useful in the normal sequence of binary numbers generated by the hardware that may cause an error or ambiguity during the transition from one number to the next. So this gray code can eliminate this problem easily since only one bit changes its value during any transition between the two numbers. Gray codes are also known as the reflected binary codes, and they differ by only one bit position, one bit binary digit. So here we can see that how to design the binary to gray code converter. Here you can see that this is the binary and these are the gray codes. Okay. So you can see that they differ by only one bit position. Okay. So here you can see this is the binary to gray code converter. So this B3, B2, B1, B0 are the binaries, and G3, G2, G1, G0 are the gray codes. Okay. From here we can see that B3 is equal to B3. Okay. G2 is equal to B3 XOR B2. The G2 is equal to B3 XOR B2.
Yes, sir.
And G1 is equal to B2 XOR B1. And G0 is equal to B1 XOR B0. So if the binary code is suppose 0, 1, 0, 1, okay.
Yes, sir.
What will be the gray code for this? What will be the gray code?
E3.
P3 is 0 means here we get 0. Okay. Now for G2 is B3 XOR B2. What value will get for G2? So it is B3 XOR B2 means 0 XOR 1. So 0 XOR 1 is what? 1. Next P2 XOR B1. B2 is 1 and B1 is 0.
Yes, sir.
So 1 XOR 0 is 1.
One.
Then G0 is B1 XOR B0. So 0 XOR 1. So we get here
1.
1. So the binary is 0101 and the gray code for that is 01 01 11. Okay. So in this way we can convert the binary to the gray. Okay. So this circuit is used to convert the binary code into the gray code. Now, how to design the gray to binary code converter? So here we are having this gray and this is the binary, okay? Gray to binary. So here G3, G2, G1, G0 are the gray codes and B3, B2, B1, B0 are the binary codes, okay?
Okay, sir.
So here B3 is equal to G3, okay? B2 is equal to what? G3 XOR G2. B1 is equal to
G2 plus G1.
G3 XOR G2 XOR G1. B0 is equal to G3 XOR G3 XOR G2 G3 XOR G2 XOR G1 XOR G0. Okay. So if gray code is what? 0, 1, 1, 1. To find out the binary code for this,
Zero.
find out the binary code. So B3 is equal to G3, so this will be equal to 0. G3 XOR G2, 0 XOR 1, so this will be equal to 1. G3 XOR G2 XOR G1, okay? So 0, 0 XOR 1 is 1, and 1 XOR 1 is what? Equal to 0. Then again, here G3 XOR G2 is 1, then 1 XOR 1 is 0, and 0 XOR 1 is equal to 1.
1.
So for 0, 1, 1, 0, the output of the binary code is 0, 1, 0, 1. Okay. So in this way, we can convert the grade to binary. Okay. Next, we'll see the logic gates. Okay. What are logic gates? So these are the digital circuits with one or more input signals, but only one output. It's called a logic gate. Okay. So it is a digital circuit with one or more input signals, but only one output is called as the logic gate. So these logic gates are the basic building blocks of any digital system. Okay. So it is an electronic circuit which is having one or more inputs and only one output. Okay. So this relationship between the input and output is based on certain logic. So based on this, logic gates are named as AND gate, OR gate, NOT gate. Okay. So the logic states can be true or false, that is 1 or 0, high or low, on or off, or plus 5 volts or the 0 volts. Okay. So these gates are identified by their functions, that is AND gate, OR gate, NOT gate. These above said logic circuits can be classified in the following categories. Okay. So the basic gates are the AND gate, OR gate, and the NOT gate. First, we'll see what is the AND gate. So what is the AND gate? AND gate is an electronic circuit that gives a high output, that is output is 1 only if all the inputs are high. Okay. So when all the inputs are high, then the output will be high. So dot is used to show the AND operation. If two inputs are A and B, so the output will be A dot B. Here we can see a symbol of the AND gate. Here we are giving the inputs A and B, and the output Y is what? A dot B. Okay. So here we can see the truth table for two input AND gate. So input is A and B. For 0, 0, the output is A dot B is 0. For 0, 1, the output is 0. For 1, 0, the output is 0. And for 1, 1, the output is 1. When both the inputs are 1, then the output is 1. Okay. Next is the OR gate. What is the OR gate? The OR gate is an electronic circuit that gives a high output if one or more of its input are high. So plus sign is used to show this or operation. Or means what? A plus B. Okay. Here we can see the symbol of the OR gate. So we are giving the inputs A and B, and the output Y is what? A plus B. So here we can see two input OR gate. So A and B are the inputs. So for 0, 0, the output is A plus B is 0. For 0, 1, the output is 1. For 1, 0, the output is 1. And for 1, 1, again the output is 1. So here we can see the symbol of the OR gate and the truth table. Next is the NOT gate. NOT gate is an electronic circuit that produces an inverted version of the input as its output. Okay. So here we can see the symbol of the NOT gate. So the input is A, output is what? A bar. If the input is A, the output is A bar. This is the NOT gate. So here we can see the symbol and the truth table for the NOT gate. If the input is A, the output is what? A bar. So if A is 0, then A bar is what? A bar is 1. And if A is 1, then A bar is 0. Okay. Here we can see the symbol and the truth table for the NOT gate. Okay. So this was about the basic gates. Now we'll see what are the universal gates. So the universal gates are what? NAND gate and the NOR gate. Okay. And the combinational gates are the XOR gate and the XNOR gate. So first we'll see what is the NAND gate. What is the NAND gate? So this is the NOT AND gate, which is equal to the AND gate followed by a NOT gate. So the output of all NAND gates are high if any of the inputs are low. Okay. The output of all the NAND gates will be high if any of the inputs are low. The symbol is the AND gate with a small circle on the output. So here we can see the symbol of the this is symbol of the NAND gate. A and B are the inputs, and the output is what? A dot B the whole bar. So for 0, 0, the output is 1. For 0, 1 also it is 1. For 1, 0, the output is 1. And for 1, 1, it is 0. Okay. Next is the NOR gate. What is the NOR gate? This is the NOT OR gate, which is equal to the OR gate followed by the NOT gate. The output of all NOR gates are low if any of the inputs are high. So if any one input is high, the output is low. The symbol of the OR gate is a small circle on the output. So small circle represents the inversion. Here we can see a symbol of the NOR gate. A and B are the inputs, and the output wise is equal to A plus B the whole bar. Here we can see the inputs are A and B. So 0, 0, the output is 1. For 0, 1, 0, 1, 0, 0, and 1, 1, the output is 0. Okay. Next is the combinational gates. So XOR gate and XNOR gate are the combinational gates. So what is XOR gate? XOR gate is a circuit which gives a high output if either but not both of its two inputs are high. If any one input is high, then the output is high. If both the inputs are low, or if both the inputs are high, then the output is low. So here we can see a symbol of the XOR gate. So here we can see A and B are the inputs, and the output is what? A XOR B. So the encircled plus sign is used to show the XOR operation. So here we can see the two input XOR gate. If AB is 0, 0, the output is 0. For 0, 1, it is 1. For 1, 0, also it is 1. and for 1 1 the output is 0. Next is XNOR gate. So exclusive NOR gate circuit does the opposite to the XOR gate. So it will give a low output if either but not both of the two inputs are high. So symbol of the XOR gate is a small circle on the output. So small circle represents the inversion. So here you can see the symbol of the XNOR gate. So A and B are the inputs, and here we are having the bubble and the output. So for 0 0 the output is 1. For 0 1 it is 0. For 1 0 also 0. And for 1 1 the output is 1. Okay. So any doubts till now?
No, sir.
No doubt, sir.
No, sir.
Excuse me, sir. Can I go to washroom? I'm Sir Prathamesh Yadav.
Who is Prathamesh Yadav? Prathamesh Yadav?
078.
What is going on? We will see the next topic now. So next is what is sum of products and product of sum. Okay. So you are knowing this, what is SOP and POS? So sum of products is the abbreviated form of the SOP. Okay. So sum of products is a form of expression in the Boolean algebra in which the different product terms of the inputs are being summed together. Okay. So the products are not arithmetically multiplied, but Boolean logical and sum is Boolean logical OR. So here we are having the product terms are your A bar B C bar, A bar B C, A bar B C plus A B bar C. Okay. So these are the product terms, and when we'll add them, so it forms the sum of products. Okay. So F is equal to A bar B bar C plus A bar B C bar plus A bar B C plus A B bar C. This is the example of the sum of products for the three variables. Okay. So this is the sum of products for the three variables A, B, and C. And what is product of sum? The product of sum expressions are the Boolean expressions that are made of sum consisting of one or more variables, either in the normal form or complemented form, or the combination of both, which are then added together to form the product of sum. So in this, we are having the product terms are A plus, the sum terms are A plus B plus C. Okay. These are the sum terms. So these sum terms are added together to form the product of sum. So this is example of product of sum is F is equal to A plus B plus C into A bar plus B plus C into A bar plus B bar plus C into A bar plus B bar plus C bar. This is the example of the product of sum. So this is for two variables. Can you give me the example for the two variables? This is for three variables. Can you give the example for the two variables?
Excuse me, sir. Please explain it again.
For two variables.
Excuse me, sir, I am Sriharpati Jadhav. Can I go to washroom or not?
So for two variables, what will be the example? F is equal to what? For two variables, the sum of products will be A B bar plus A bar into B, okay? A B bar plus A bar into B. This is the example for the sum of products. And what is product of sum? For the two variables, you can write F is equal to A bar plus B into A plus B bar. Okay. The example for the POS, product of sum. Okay. Yes or no? Any doubt in this? So next we'll see what is the min terms and the max terms. Okay. Min term, so logic term that is consisting of all the literals in the ANDed form is known as the min term. So here we have taken the 3 bits, means X, Y, and Z. So for this, we are having the min terms from M0 to M7. So min terms are what? They are the product terms. They are in the logic term consisting of all the literals in the ANDed form is known as the min term. So for 0, 0, 0, the min term is what? X bar dot Y bar dot Z bar. For 0, 0, 1 is equal to X bar dot Y bar dot Z. For 0, 1, 0, it is X bar dot Y dot Z bar. For 0, 1, 1, it is X bar dot Y dot Z. For 1, 0, 0, X dot Y bar dot Z bar. 1, X dot Y bar dot Z. For 1, 1, 0, X dot Y dot Z bar. For 1, 1, 1, X dot Y dot Z. Okay. These are the min terms for the three variables X, Y, and Z. And the max term will be for 0, it is considered as X, and for 1, it is considered as X bar. Okay. So min terms are represented by small m, and max terms are represented by the capital M. Okay. So these are the max terms. For 0, 0, 0, max term will be X plus Y plus Z. Okay. These are the for the three variables. So what will be the min terms for the four variable? Min term for four variable. Four variables A, B, C, D. Suppose the binary number is 1011. What will be the min term for this?
A B dash C D.
Yes, A dot B bar dot C into B. Yes, correct. And what will be the max term?
A bar plus B plus C bar plus D bar.
A bar plus B plus C bar plus D bar is correct. This will be the min term and the max term for the 4 variables. The binary we have taken, binary number is 1011. Okay. Next we'll see what is the K-map. Okay. How to minimize using K-map up to 4 variables with don't care condition. Okay. What is the K-map? It is a method used for simplifying the Boolean algebra. Okay. Used to simplify the Boolean algebraic expressions. So it was developed by the Karnaugh in 1953. Okay. So here you can see this is a 2 variable K-map, this is a 3 variable, and this is a 4 variable. Okay. So in the 2 variable K-map, we are having the 2 A and B are the 2 inputs. So A can be either 0 or 1, and B can be either 0 and 1. So for 2-bit input, we are having 4 combinations, that is 0, 0, 0, 1, 1, 0, and 1, 1. And in the 3 variable K-map, we are having the 3 inputs A, B, and C. So we will have 2 raised to 3 combinations, that is 8. That is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay. And for the 4 variable K-map, we are having the 4 inputs A, B, C, D. So we'll have the 2 raised to 4 combination, that is 16. That is from 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. So this will be the 16 combinations for the 4 variable K-map. Okay. So here this 0 means what? This is the 2 variable K-map. For this, this 0 means it is 0, 0. Here this 1 means it is 0, 1. 2 means 1, 0, and 3 means 1, 1. For these values of 0, 0, what is the output that you have to put in the K-map? Okay. Then we have to group the number of ones, and after that we can simplify the Boolean expression. Okay. So these are used to simplify the Boolean algebra. Okay. These are different types: 2 variable K-map, 3 variable, and 4 variable K-map. Then we can put the values in that, and we can simplify any Boolean expression. Okay. So here we are having, suppose this is a truth table for the 3 variables A, B, and C, and the output Y is 0 or 1. So if you want to put these values in the K-map, how to put them? So for 0, 0, 0, the output is 0. For 0, 0, 0, 1, the output is 1. For 0, 1, 0, it is 1. For 0, 1, 1, it is 0. For 1, 0, 0, it is 1. For 1, 0, 1, also 0. For 110 it is 0. For 111 it is 1. So this ones you can put and then you can group the ones and you can solve this. Okay. How to simplify the expressions? We will see in the next class, okay, the minimization techniques using K-map. Okay, how to minimize any Boolean expression by using the K-map, we will see in the next class, okay. So CR, can you tell me who is absent?
All are present, sir.
Okay. Okay, then that's all for today. We'll meet in the next lecture. Okay, thank you.
Okay, sir. Thank you, sir. Thank you.
Jai Hind, sir.
Okay, welcome.